we've talked about single or synthesis, decomposition, and single replacement reactions. So synthesis reactions do what? How can we tell it's a synthesis reaction?
They combine.
It's two elements before the arrow combine to form a compound. Decomposition, how do we know it's decomp? This is page 12.
Is this page 4 on this one?
Yes. We didn't do the front part. We're starting at double replacement. Okay. So the decomposition is when they break apart, right? We have a compound that breaks apart into two elements. And then single replacement is what?
Replace.
An element and a compound. Now with single replacement reactions, we have to use something called a what? Do you remember the list? The RIS list?
Oh, yeah.
Who's got more RIS, right?
Lithium.
It's called an activity series, right? So lithium's got the most RIS, gold ain't got no RIS, okay? So in single replacement, the element that's by itself has to be above the element in the compound for this to occur, right? It's got to have more RIS, therefore it can still, its partner, okay? Now, double replacement reactions, the cations and anions of two different compounds switch places, making two totally new compounds. Okay, so in double replacement reactions, it is just two compounds before the arrow. We have written the formula equation for double replacement, and we have used solubility rules. So do you remember the solubility rules? So if you look on page 3, so page 3, we have our solubility rules. Okay, so when we do double replacement reactions, we've actually done them by writing a formula equation and using the solubility rules to determine if it's a aqueous or a solid. Okay. Now, with these double replacement reactions, so what they do is they switch partners. So here we have AX plus BY is going to give us AY plus BX. They switch places, okay? X and Y switch places. I usually like to switch the metals just because they're in front, right? But you can do it either way. Now, these reactions are never redox reactions. Okay, these are never redox reactions. Single replacement are always redox reactions. Synthesis, decomp, there it depends, okay? Now, how do I know I have this type? You're going to look for two compounds as your reactants, a compound plus a compound. So we've done element plus element, just a compound before the arrow, element plus compound, and then this is compound plus compound. Now, all double replacement reactions will either be a precipitation reaction. Okay, it's either going to be a precipitation reaction where a solid is formed. Okay, it's a precipitation reaction where a solid is formed from two aqueous solutions, or a neutralization reaction. It can be a neutralization reaction where water is formed from an acid and a base. So y'all remember when we were doing the formula equations, I said put H2O and I said put an L, because that means that's new water. Okay, so in neutralization reactions, we have an acid, which we know it's an acid because it says acid, and a base. A base is going to be a metal hydroxide. Okay, base. So an acid reacting with a metal hydroxide, that is a base. These are going to create new water. Okay, and this new water is actually behaving as hydrogen hydroxide. You're going to write it as HOH. Okay. Also, if you write it water as HOH, it's going to be easier to balance. Okay. But in these reactions that water is formed, you're not going to put it as aqueous. You're going to put it as L. Now, I used a cursive L. Okay, because if I just put a regular L, it's going to look like a 1. So, you're going to put an L to indicate that it is a liquid. Okay. Now, a reaction, says if both products are aqueous, okay, if both products, not reactants, but products are aqueous, then it's no reaction, because that's just basically like mixing two, I don't know, sodas together. Say you mix Sprite and Coke together. Does a reaction occur? No, it's just Sprite and Coke mixed together, okay? That's the same here. If you mix two elements together and it's just aqueous for both, they're just mixed together. Nothing was formed, okay? Solid, liquid, or gas has to be formed for a reaction to occur. So, if both products are aqueous, the reaction is no reaction, okay? Now, let's talk about net ionic equations, okay? So, this is basically what is happening. I'm going to scroll down. This is basically what is happening in a reaction, okay? So what's happening here is that we have our reactants and products. So basically what happens is you have solid sodium chloride, that's table salt, right? Table salt by itself is just a solid, okay? But if you dissolve it in water, what actually happens is any salt, this applies to any salt that's soluble in water, what actually happens is it separates out into its ions, okay? So solid sodium is going to dissolve in water and it's going to make this sodium chloride solution. Same with silver nitrate, okay? Silver nitrate is soluble in water. And so when I mix silver nitrate, it's going to separate out into the silver and the nitrate ions. Now, it would be according to the ratio from your formula. So, if you had something like CaCl2, it would be 1 calcium to 2 chlorines. Okay? And so, basically what happens is you're going to mix these two together. So, you're going to pour them both in the same beaker. And what's going to happen is the silver from the silver nitrate and the chlorine from the sodium chloride are going to combine to form silver chloride. Now, if you look at your solubility rules, silver chloride is a solid, okay? It is insoluble in water. According to your solubility rules, silver chloride is insoluble in water. And so that's what that is. It kind of represents it kind of sitting at the bottom like sand. But sodium and nitrate are still there. They're just kind of floating around because sodium nitrate is soluble in water. Okay? Now, what complete and net ionic equations do is that they kind of give us an idea of what's going on here. Kind of like here, it gives us an idea, but it is written in kind of a formula form. Okay, so here we have our original equation. This is the reaction we just looked at. We have silver chloride aqueous, sodium chloride aqueous, silver nitrate aqueous, yields sodium nitrate aqueous, and silver chloride solid. Okay, now when you are writing a complete ionic equation, any compound that has AQ next to it, you are going to separate it out into its respective ions, okay? So sodium chloride, I'm going to separate it out into sodium and chlorine, okay? Now notice it's a 1-to-1 ratio. There's not a coefficient in front of here. If there was, say there was like a 2 there, that 2 would distribute to both. It'd be 2 sodiums and 2 chlorines, okay? But here it's sodium ion, chloride ion, and we're going to keep that AQ next to it because they're dissolved. They're still in the water. They're just separated out. And then silver nitrate is aqueous. So we're going to have the silver and the nitrate. Now, again, one thing you want to notice is make sure you're putting those charges with it. Okay, we're showing that they separated out into their respective charges, and then again put that AQ next to it. Now, sodium nitrate is aqueous, so we're going to separate it out into sodium and to nitrate. Okay, separated it out into their respective ions. But notice, silver chloride is a solid, right? If it is a solid, liquid, or gas, you're going to keep it together when writing the complete ionic equation. So notice we didn't separate out silver chloride into its ions because it's not dissolved in the water. It is together as silver chloride. Okay? And so the next step, so that is our complete ionic. So it has all the ions there. Now the next step is writing our net ionic. Now you've seen this word, the spectator ions, okay? Basically what spectator ions are is the ions that don't participate in the bonding. Just like if you were a spectator at a Dallas Cowboys game, okay? You're sitting in the stands, you're not participating in the football game. Dak Prescott's on the field participating in the football game, okay? And so, in this case, if you look, you're about to see up there, but if you look, the sodium and the nitrate are not participating in the reaction, okay? They're just sitting there, they're just chilling. So to figure out what the spectator ions are in a complete ionic equation, you have to look at both sides of the arrow. And the ion, not just the element, the ion has to be on both sides of the arrow. So in this case, I have sodium +1 on the reactant side, and I have sodium +1 on the product side. That is considered a spectator ion. Look at chlorine though. I got chlorine -1 on my reactant, but notice chlorine -1 is not in my products. I have it with the silver, but it has to be chlorine -1. It has to have its charge with it, okay? So chlorine is not a spectator ion. Silver is not a spectator ion, okay? Nitrate, NO3 -1, is on both sides of the reaction. It's on our reactants and our products. That is considered a spectator ion. So sodium and nitrate are spectator ions. When writing your net ionic equation, what you're going to do is you're going to take those spectator ions out of your complete, and then you're going to write down what's left. What you're doing is you're writing down the ions that are reacting together to form the precipitate. Okay? So you're taking those ions out and writing down to form the precipitate. And the spectator ions are the sodium and the nitrate. So again, here's a good picture that shows that, right? We have, before the reaction, they're separated out. We mix them together, the silver and chlorine come together. Those ions are not floating around. What's floating around is the sodium and the nitrate. You're just chilling. Those are the spectator ions. Okay? So let's look at some examples. So it says, for each of the following, write a balanced reaction with states. Determine if each reaction is a neutralization, precipitation, or no reaction. And for any reaction which occurs, construct both a complete and net ionic equation, as well as identify the spectator ions. Okay? So, let's look at this. It says a solution of potassium nitrate reacts, oh wait, where'd it go? Solution of potassium nitrite, is reacted with a solution of 10,2-fluoride. So first I'm going to write my formulas. Potassium nitrate. Now potassium's charge is what? +1. Okay? Now nitrite, the whole thing, what is it? Formula and all. NO2 -1. Okay? NO2 is nitrite, right? So our formula is going to be KNO2, 1-to-1 ratio. Now, we need to use our solubility rules. Okay? So we're going to flip to page 3 to do solubility rules, because we got to see if this is aqueous or a solid. So looking at our solubility rules, potassium is a group 1 metal, right? Group 1 salts. It says all group 1 salts are aqueous, right? There are no exceptions. So if it has a group 1 metal at the beginning, automatically aqueous. So this makes this automatically aqueous. Okay? Now, it says it's reacted with a solution of 10 to fluoride. What does this 2 mean? Positive 2. That's the charge of the 10. And then fluoride is just fluorine with a negative 1 charge. So our formula is going to be SnF2. Okay, 2 fluorines to the 110, right? Do y'all see how important it is to use, you know how to write a formula? It's not going away. Okay, so when looking at our solubility rules, we don't see a rule for 10, but we see a rule for fluorine. It says all fluoride salts are aqueous unless they're bonded with magnesium, calcium, strontium, barium, or lead. If they're bonded with one of these, then it's a solid. But 10 is not in this list, is it? So that means that 10 to fluoride is what? Aqueous. Okay, 10 to fluoride is aqueous. Now we predict. So in double replacement reactions, they just switch, right? So I'm just going to switch the potassium and the tin. Now when I switch them, I have to pay attention to those charges, right? So when I switch them, I get KF, but I got to double check my charges. I have potassium positive 1, fluorine negative 1. So KF is correct. It's not always going to be correct, right? You're not going to put CAN. Okay. Plus KF plus SN. Now 10's charge is positive 2. Nitrite is negative 1. So that means I'm going to need 2 NO2s to balance that out. Okay? Now KF, check your solubility rules. KF is what? Aqueous. Why is KF aqueous? There's no exceptions, right? It's group 1 potassium, no exceptions. Now tin nitrite, I don't see a rule for tin. I don't see a rule for nitrite, but I do see a rule down here. It says all other monoatomic and polyatomic anions, that includes nitrite, are solids unless bonded with group 1 and ammonium. Now in this case, it's not bonded with group 1 and ammonium. So that means that nitrite, tin to nitrite, is what? A solid. Okay, there's an exception. Now, since it's a solid, what was I going to say? Man, I left my brain. Oh, did a reaction occur? Yes, a solid was formed, so a reaction occurred. Now we need to balance it. Okay, so we got 1 potassium, 2 fluorines here, so that means I need to put a 2 in front of the potassium fluoride. That changes my potassium, so I'm going to put a 2 in front of potassium nitrite. And that balances out the nitrites, and then the tins are good. Okay. So, what goes in front of the tin fluoride? Tin 2 fluoride? What number? 1. Okay. There's an understood 1. If there's a blank there, there's an understood 1 there. Do not tell me there's 0. If there was 0 tin 2 fluorides, this reaction would occur. You're telling me it's not even there. So, there's at least 1. So make sure you are. You don't have to write the ones in front. I highly encourage it. Because you're going to be using that one next unit for conversions. Okay. Now I'm going to write my complete ionic equation. In complete ionic equation, the compounds that have AQ next to them, I'm separating them out into their respective ions. Okay? So, I got potassium nitrite. Okay, I'm going to separate that out. So it's going to be 2 potassium ions, aqueous. Now this 2 is going to distribute to the nitrite 2. Okay, so plus 2 nitrite ions. Okay. Now separate the tin to fluoride. Plus 1 tin okay, because there's a 1 in front. Plus, now this 2 here for fluorine is just going to affect the fluorine, but you're going to bring that out front, okay? Plus 2 fluorine ions, okay? So what that is a ratio. It's a 1-to-2 ratio, okay? Now, that's going to yield, okay, Kf is aqueous, so I have to separate them out. 2 potassium ions plus 2 fluorine ions. Now, if it's a solid, do we separate those out?
No.
No. So the tin nitrite, SnNO2, 2, solid, you're going to keep together. You do not separate that out. Okay? Now, to write our net ionic, we have to find our spectator ions. Those are the ions that are on both sides. So I see potassium, I see 2 potassium positive ones here, 2 potassium positive ones here. So that is a spectator ion. Now I see 2 nitrites here, nitrite ions, but I don't see the ions on my product side. Same with tin. I see a tin ion here, but I don't see it on the product side. I see 2 fluoride ions here, 2 fluoride ions there, so they are spectator ions. Now what's going to happen is when I write my net ionic equation, I do not include the spectator ions. I'm just going to include the ions that participate in the reaction. So I'm including the 2 nitrite ions plus the 1 tin ion yields tin to nitrite. Okay. Now notice how writing your formulas correctly affects the balancing, it affects the complete and net ionic equations.
Isn't NO2 -1 by itself a solid?
What?
NO2.
Yeah, it's nitrite ion. It's not nitrogen dioxide. Is that what you were asking?
Do you still do that as a solid form?
No. It's dissolved in the water. What it is that you have a beaker, and I put in the potassium nitrite, and that separates it out into the potassium ions and the nitrite ions. The solubility rules apply to compounds, not individual ions. Yeah. So it's like if the compound has this ion, then it's aqueous or solid. Okay. Now let's look at the next one. Oh wait, last thing, we gotta label it. Duh. What kind of reaction is this?
Precipitation.
This is a precipitation reaction. How do we know it's a precipitation reaction? Because it made a solid. Okay? 2 solutions came together and made a solid. That makes it a precipitation reaction. Okay? The net is the one without the spectator. Yeah. All right, next one. Hydrochloric acid is mixed with a solution of calcium hydroxide. Okay? So, hydrochloric acid. Acids always have what as their cation? H positive 1 is always their cation. Now, if you have hydro in front, that tells me that my anion is what? Ide, meaning it's just the element, right? It's not a polyatomic ion. If there's no hydro in front and it ended in ic, what would it be? 8. If there's no hydro in front and it ended in ite, it would be in, if it ended in us, it would be in ite. So hydrochloric is chlorine. Chloric would be chlorate. Chlorus would be chlorite. Okay? So our formula here is going to be HCl. Now, acids are always aqueous. That's what makes it an acid and not hydrogen chloride. Okay? Plus, now it says a solution of calcium hydroxide. What's calcium's charge? plus 2. Hydroxide is OH negative 1. So our formula is going to be CaOH2. Okay. Now if you look on your solubility rules, calcium hydroxide is an exception. Mostly all salts of a hydroxide are solids, but if it's formed with calcium, it's aqueous. So that means calcium hydroxide is aqueous. Yes? No. Yeah. Okay, so now switch it up. Calcium and hydrogen are going to switch places. Now remember, when they do, though, you have to account for those charges, right? So you're going to form calcium chloride, but is that the formula? No, because calcium is a positive 2, chlorine's a negative 1. So it's going to be CaCl2. Now, what state is that going to be in? Look at your solubility. All chlorides are aqueous unless it's silver, mercury, or lead. Okay? Is it silver, mercury, or lead? No, then it is aqueous.
Why are you switching the H and Cl? Why is not the Cl in the hydroxide?
Because H is considered the cation. You're switching the cations.
Oh.
Yeah. You have to have cation, anion, cation, anion. So what you'll be left with is hydrogen hydroxide, which is also known as water. Now this is going to be a liquid. This is when you put the L. Okay. What kind of reaction is this? Neutralization. This is a neutralization reaction. Okay. Neutralization reaction. Now, balance. We're going to balance. So, now in this case, since I wrote water as HOH, I can keep the hydroxides together, and it makes balancing a lot easier. Okay. So 1 hydrogen, and then just count this one in front. 1 hydrogen, 1 chlorine, 2 chlorines. Okay. So I'm going to put a 2 in front of the HCl. Okay. That changes the hydrogens though, so I got to go back and balance the water. Put a 2 there. So that changes the hydroxides to 2, which balances it out, right? We have 2 hydroxides here, 2 hydroxides there. Calcium, we got 1 calcium, 1 calcium. So again, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, 1 calcium, 1 calcium, 2 hydroxides, 2 hydroxides. So we're balanced. So what would go in front of the calcium hydroxide and the calcium chloride? 1. Okay, it's an understood one. Now, we're going to write our complete ionic equation. We've got 3 aqueuses and 1 liquid. So if it's a solid, liquid, or gas, that's when you keep it together. So we got 2 hydrogen ions, well, H plus 2 chloride ions, plus 1 calcium ion, plus, now this 2 is going to be 2 hydroxides, okay, so separate out those ions. Yields calcium chloride is aqueous, so we got 1 calcium ion plus 2 chloride ions plus water, because that is a liquid, we're keeping it together. HOH stays together.
You don't put the coefficient
Oh.
minus 1.
What?
You don't put a 2 H2O.
Oh, yeah, you do. Sorry. 2 H2O. Okay, so now we want to go through and check our work. So we're going to go through and check. We have, we want to see what the spectator ions are. So we got hydrogen ion over here on the reactant, but we don't have any in the product. We got 2 chloride ions in the reactant and 2 chloride ions in the product, so that is a spectator. We got 1 calcium and 1 calcium, that's a spectator. 2 hydroxides and hydroxides and all the products, that is part of the net. Okay, so it's only if the ions are on both sides does it cancel out. Okay, so it's going to be 2 chloride ions. No, wow, it's been a day. That's the spectator, duh. Okay, so we got 2 hydrogen ions plus 2 hydroxide ions yields 2 waters. Okay, now in this case though, we have each coefficient is 2, so you can just reduce each coefficient to 1. Okay, if all your coefficients are positive, reduce it. Okay. Now the last one, it says solutions of sodium acetate and 10,2 chloride are combined. So, I'm going to write our equation. Sodium's charge, +1, acetate is C2H3O2, -1. So our formula is NaC2H3O2, aqueous. Okay? Plus 10,2 chloride, so SN, that SN is +2, chloride is chlorine -1, so it's SnCl2. And that's going to be aqueous also. How do I know that? How do I know sodium acetate's aqueous? We got a double whammy here. We got group 1 salts, always aqueous, no exceptions. Also, acetate, always aqueous, no exceptions. Okay, so they're both aqueous. Then 10,2 chloride, chlorine's always aqueous unless bonded with silver, mercury, or lead, and then it is solid, but it's bonded to 10, so it's aqueous. Now, when I switch these, I get sodium chloride, which is aqueous because group 1 metal, and then 10,2 acetate, which is also aqueous. So did a reaction occur here? No. This would be no reaction. Why didn't it occur? Everything is aqueous, right? They're all just chilling and hanging out. Nobody's doing anything. Okay? No reaction. It's like if you mix Sprite and Coke, nothing happens. Okay? Questions about that? Great.